All right. Now, we are going to now talk about the single degree of freedom equations of motion. Let me write it down because I have a reason. DOF motions in waves, regular waves of course. See the here the catch what you will find is single degree of freedom. Okay. Now, let me before going to this, let us talk about the motions itself. Now, you see in the last lecture we saw that if I have a ship, the excitation F, if I call it the wave induced force, would have a periodicity of omega e, that is it will be something into cos omega e t plus maybe some phase gap. In generally it will look like that, the excitation. Okay. This is we do not know, this is whatever the excitation is, but what we know here of course is that it will have a periodicity of omega e, because at omega e it is coming. So, generally therefore, since it is sinusoidal with one harmonic component, we would expect all the motion displacements to be also of similar form. So, I can expect for example, all the motions, if I were to call, now I can call in a index form, let us say x, y, z, I am calling it as 1, 2, 3, and about x, y, z I am calling 4, 5, 6 to be the indexes defining those. So, this becomes, see this becomes some amplitude into cos omega I e t plus phi xi I, something like that. It will look something of this nature. Okay. In fact, I will just elaborate that on that. For example, we will have a surge motion I can call say x a cos omega e t plus let us say e, these are phase angle, so I can call it this x equal to y equal to y a, etc. Let me write it down only. Heap roll is normally called phi . This is phi theta. See, I have a reason for writing this entire thing up, although it is repetitive. Now, you see here on this modes of motion, which is important for us, that is why I wrote all this stuff. Now, think of this, there is a ship here, somehow it got moved in forward because of a force. Will it come back? How much will it come back, etc. Question is that in horizontal plane, that is this, this and this, I have nothing restoring force, that is if I pushed it, fluid do not, the hydrostatic force do not try to pull it back. Okay. So, from a point of view of motions, it becomes less important, because it, in other words, the ship is neutrally stable in the horizontal plane. On the other hand, it is heave, roll and pitch, where if I for example heave the body, if I pushed it down, then it will try to come up and there is an oscillation, and as you know, if there is a restoring force, then there is a chance of resonance. We will come to that subsequently. So, what happened for us, an important modes of motion becomes these three. Okay. Now, you see, now what is happening is, remember that the entire motion is defined if I know two things, one is the amplitude one is the phase. Then I know full thing. How? We will see that. Let us take an example of roll or something. So, what is happening? See, remember I have put a phase. So, let us put the first of all wave eta. Now, we are normally writing eta at origin. This is, let us say, eta at origin. See, remember, eta is function of x and t. What is eta? It is a function of a cos kx minus omega t, or rather okay. Obviously, it depends on x. So, when I try to talk of phase, or when I draw with respect to t, I must have some x. So, normally what happens? I am plotting this at x equal to 0, let us say. That is origin. So, we are always measuring once again this phase angles. I told you that it is only a question of difference between some signal. So, you can measure that with respect to some signal. Normally, we are going to measure it with respect to the wave crest at origin, which means the wave eta signal at x equal to 0. Let us say it is looking like this. See, this is the cos curve. Okay, you know, if you take x0, it is a cos minus omega t is a cos omega t. Anyway, minus theta is theta. Now, what would happen? This signal therefore would look something like, let us say this is where this gap, this is a measure, I am not writing, this is a measure of my phase angle. Now, if this was, for example, my roll, that is, it is my phi a cos omega e t plus epsilon phi, then this is in some sense measure of E phi, not exactly same. Remember that there should be t and all that part. I am just trying to give a concept of that. So, you see, now the point is that I would know what is my time history, all the points on this, but I know the entire thing if I only know two things, that is the amplitude and that is its location. In fact, this E phi basically sets me where the origin of this is, the starting point of the signal. This E phi fixes the position of the signal in the t axis in principle. In the t axis, it tells me from where it starts, that is my phase, and the amplitude tells me the amount of maximum. So, what is happening in any case? See, this is phi t. You know, if I know this and if I know this, of course, omega e I know because omega e is my input. So, I can find out phi at t at any point. You can run a program at t, the 0 second, 1 second, 2 second, 10,000 second, 1 million second, you get the graph. So, only thing is that you need to, but where it comes from is, that is what I was trying to tell, that E phi phase sets its location where it is starting from with respect to the wave crest or with respect to some measurement, and the other one that gives you amplitude. Now, you see, let us take me, this is, let us call it, you know, roll, then let us now, or some other signal, it can be pitch also, but let me also take now another one, let us say heave. So, heave will look like, say, something like that, where this will be the measure of the E z, the heave signal phi. So, all of them, all the ship motion, if I look at that, would have all these components, its own amplitude and a phase, and between these two, if I want to find out what is the relative phase of heave with pitch, it is E z minus E phi, etc., etc. Now comes the concept of single degree of freedom equation of motion. So, now we know the motions, of course, before I go again, once I know this motion, see, it is very easy for us to find out the velocities and accelerations also. How? Because any of them, if I differentiate that, it will simply become like omega into phi, etc. For example, maybe I will just do it here before I go to single degree. See, if I for this, if I were to do roll velocity, that is phi dot t, what it becomes? It becomes minus omega e phi a sin omega e t plus E phi, right? And if I take acceleration, it becomes minus omega e square phi a cos omega a t plus E phi. If you look at this, cos curve would have been, well, in another reference like this. This is my displacement. Velocity would have been a negative sine curve, that is this way, and acceleration would have been a negative cos curve, that will be this way. So, you know, my point of view therefore to tell you is that actually if I know this and if I know this, I would have known everything that I need to know as far as roll motion is concerned or a particular single degree motion is concerned in that particular single wave. Remember, omega e is a function of what all thing? Ship speed v, heading mu, and of course wave frequency omega. We have seen that omega square equal to, in last class, omega square equal to omega e equal to omega minus omega square v by g cos mu. So, for a given ship speed, for a given wave heading angle, for a given regular wave of any length, I know omega e. This is my environment. I have a given wave coming from a given direction in which my ship is moving at a given speed. So, I know omega e. What I want to know, therefore, what is my motion? Well, I now say my ship was going to move in this fashion and I need to know my amplitude of the motion and the phase. And once I know this, I can find out its acceleration, I can find out its velocity, I know the entire thing, there is nothing more I want to know. How do I do that? That is the question number one, is how do I do that, which is what we will discuss. But does it occur singly? That is another question that we have to answer. What is meant by single degree of freedom equation of motion? Now comes this question. See here, I will give this example right from your Hill case. Now, let us take a body here, Now, you know, say this was my point G, or let's take only this point as my origin. It's easier. Now, what has happened if I held it? Okay, you know all that if the angle is little large, this will not go through pass through, this will pass through somewhere else, which would imply that if I were an experimental device, if I fix this point, you know, somewhere at some location, if I held it, this point will try to either go up or go down. Agreed? Because underwater volume has to remain constant. Now, I have defined this angle to be roll. So, I see that as soon as I rolled or held, there is an heave coming up because the full thing is moving up. So, I cannot have an isolated roll. Roll is necessarily inducing heave. Heave may not induce roll because if I push down it is okay, but roll is inducing heave. This is what is called coupling. That means when I sum of the motions, and in fact strictly speaking all the 6 motions are coupled, if you induce one, the other will come. Of course, what would happen, there are some decoupling that we will see afterwards because of symmetry, etc. But in a general sense there will be coupling between some modes of motion. Actually, a better example is heave and pitch always. You know, if I take this body here, since it is somewhere here, we all know it also, that when I want to, this question I always we have discussed that even in hydrostatic, and the question that we ask is that supposing I shift a body from here to here, then can you say that there will be no change of draft at all? One cannot say that, because what happened, the trimming is over LCF position, draft is measured typically at some other location midship or so, there the draft is changed. So, what I am trying to therefore say is that if I call the draft to be a measure of heave, then if I give a trim, then I also have a heave, right. And same thing will happen if I have a parallel sinkage, as you know it trims, because if I have a parallel sinkage, then it will it's just like this is the question, same as when a ship moves from salt water to fresh water, etc. As you know, it will always have heave and trim. So, in other words, if I in a vertical plane, in this vertical plane, if I want to displace the hull, automatically both the vertical displacement and the rotation gets induced. This means heave and trim or pitch, I will call, actually the word trim is a static pitch, heel is a static roll. That is if you do not move it, but we are now gone to a next level where we are time dependent. So, we find out that these two are coupled typically. Now, this is practical example shows that there is no way you can decouple it, I mean strictly speaking, even if it is very small. And if you go theoretically, all 6 modes of motions are always coupled. That is how you should start. Of course, we can like reduce it. Now the question comes is like this. Some of the modes we know are not coupled. How? I will tell you an example. Let us say surge. Now body is symmetric. So if I shift it this side, there is not going to be any motion this side. So my surge will not induce any motion in sway direction. So surge and sway are decoupled. Similarly, there are modes. Similarly, surge will not give me heave or trim like that. But we also know some modes are coupled. So in particular, heave and pitch are very much coupled. But when we talk of single degree freedom, what we are saying is that, in fact, roll also we may add. What we are saying is that, look, before I study more complicated coupled one, since the coupling is not all that strong, it is only small, we can study the characteristic by assuming there is no coupling, by presuming that if I make it, if I were to heave it, the trim is so small I can ignore it. So this is what is meant by single degree of freedom equation of motion, and it is good enough, because remember that when we are studying, we keep making rational simplification from the beginning. First of all, we said the waves are small amplitude, then we said in the defining motion also we said motions are relatively small compared to the length of the vessel, etc., etc. So it is not inconsistent to study by itself a single degree freedom equation of motion. So this is the full point, therefore, is that when I say single degree freedom equation of motion, we are decoupling it, we are trying to in isolation see, we are saying that supposing the vessel has a mode of motion in this particular plane, then it is not having motion in any other plane, or it is not inducing. This is what we are trying to actually say. Okay. So this is where the concept of single degree freedom equation motion, and what is happening is that any equation of motion you are going to write mass into acceleration equal to force. What we are saying here is that if I were to accelerate the body in heave, for example, it is not going to get a force because of the consequent pitch or trim. Everything is only heave. If it heaves, it only heaves, it does not trim. If it trims, it only trims. This is what we say, or obviously at the first step we must study this, because the coupling is very weak usually. There are cases when coupling is very strong, but when you are studying, first we study single degree freedom equation, then we study primarily heave, pitch and roll, because these three are the most important sea keeping motions. Then we will see whether we can couple it, and we will have an idea regarding its coupled modes of motion. Okay. So this is how we actually kind of proceed. Now let us now go to how does a single degree freedom equation of motion look like. Okay. Now I would like to give you a little bit of kind of physical scenario of what happens when a ship moves, etc., etc., where the forces and all come from. See, now I take one more picture, the wave here. Okay. Number one, let us understand this. This is only component build up that I am trying to tell, and I will request you to pay attention to that, because it is a build up part. See, Newton has said many years back that, and it is all Newtonian mechanics, that mass into acceleration is equal to force. So we have got, say, mass into, let me take an example, heave as an example, z or something. So acceleration is this equal to, what is this force? Now everything is because of this force coming. Now you see this force. let us say that this ship was transparent to the waves. That means this line remains as it is even if I put the ship. Let us imagine a case that I have removed this ship from the water. The water line is black line. There is a pressure there, and I think there is pressure there in that hypothetical surface. Now I put the body. Okay, and then I presume as if the body did not disturb the water. What would happen is that number one, a primary force would be on the hypothetical position. Let us say this is the hypothetical position of the hull. All these points, there are pressure that we have found out yesterday, linear water wave pressure. So, of those pressures, I add it all up. After all, force equal to pressure into N into ds over the surface. Okay. Then I will get one component of force. This is one force, let me call this force num. Now this pressure has two components, but I am talking of the dynamic incident wave pressure. So I end up getting the incident wave, I am calling this as Fi. Again in principle, this would be the force arising because of the incident wave pressure at those location. Okay. That is that rho d phi by dt, where phi is only phi I. Why phi I? Because we say that the body did not disturb the waves. So I have a body and I simply find out if the body was there this location, what would be the pressure, so I add it all up. That is one part. However, what has happened, we all know that the water is fully changed. Reason is very simple. Again, I have this body here, waves was going like that, in another plane. Now, actually this is all going, okay. Now the point is that this particle is moving in a circle, but it cannot move in a circle because if it is moving, if I allowed it, then the particle would have penetrated my hull. So what has happened is that obviously that another wave system must have to be created on the other side so that it nullified that inward motion to outward motion, so that my pressure point here remains stationary, not stationary, did not move normally inside. See, it is very interesting point to know, and this is where the question of this yesterday's 0 equal to 1 minus 1 comes in. See, let us say here this point cannot have a motion this side, normal direction inward. I am talking once again, I am only trying to explain the concept conceptually rather than with a strict maths. See this, let me put it again here. This is my hull, this is the point here, this is the point here, I am just looking. Now this particular point has at a given instant of time, let us say at a given instant, fluid motion this side because it is the crest location. Okay. If the body was not there, the particle would have moved, have a velocity this side, right. But if the body is there, it cannot have velocity. How much the velocity should be? 0 and normal. That means how can I get a 0? If I introduce another motion opposite side. How do I do that? Provided I impose another wave on the opposite side. See, if I induce another wave opposite side, then it becomes 0, almost 0, again in principle. So what is happening? Obviously this would have disturbed and made it 0 means I can imagine that it would have created one more wave system just opposing the phase of this wave here, so that the particle cannot go in. So therefore this picture would have got changed and I would have got created one more wave system countering it if I kept it fixed, let us say. So what is happening? This wave I call it diffracted wave, scattered reflection, it is like wave reflection. Similar to that, in our in hydrodynamics it is known as diffraction or scattered because it can be in any direction. This is the same thing as light comes on a particle, gets scattered. Similar explanation, you know why sea is blue, etc., etc., sky is blue, etc., etc. So there is a wave creation. So some effect is 0 for this point. So now that wave obviously would have altered the pressure field, because the pressure is now no longer d phi I by dt because there is another phi. So that we call it diffracted force. Remember, in this now there are again two scenarios. I presume that as if I have hold the body fixed, I did not allow to move. I fixed it, I kept it, somebody is holding it by a hand, wave comes, particle cannot move, so it must have created a wave back. This is one part of, so this gives rise to one component, and obviously it will add up to one force. We call this actually say FD, diffracted force, similar to reflection, but there is more to the story. Now, but I am not holding it fixed, the body is oscillating. Now you take this case, I have a calm water, okay. So I have a calm water somewhere here. Now I took a body and I oscillated that. What would happen? It would create some waves. You can, anybody can try that and see. In a calm water I took a body and I oscillated, it will create a wave. Now here what happened? Net effect is that the body is moving, but if the body did move, it would have created one more system of waves around it, because any free surface you oscillate, it will create one more system of waves. Now if it created this system of waves, again that will create a pressure field. In fact, it is very obvious to see that the energy that you input, that creates the waves, and that's, you know, that energy gets dissipated in forms of waves. So obviously there is a pressure field introduced. That is one more kind of waves that comes in. This is known as radiated waves, you know, radiation waves, or another wave, let me call it FR. I mean, when I say FR, please understand, it implies all effects connected to the wave system created by oscillation of the hull in a otherwise calm water. So I end up getting this. Remember also that there is also hydrostatic pressure standard, because you see, if I were to take the shape from here, from here, I pushed it down to this much, this extra hydrostatic pressure comes in. So there is an hydrostatic force also. See, my shape is having a static draft of 10 meter. If it went down to 11 meter, I have that rho g AWP into that 1 meter pushing it up. That's coming purely because of the hydrostatic pressure rho z z. So there is another hydrostatic pressure rho this thing. So this side therefore composes of this force, this force, this force, this. In fact, we are able to do this because of linearity. Because of linearity, I can say, as I said here, 0 is 1 minus 1. This is why we are saying that this scenario, nature will not tell us, nature will simply show some wave here. We are only saying that this wave is composed of, or can be broken down into this and this and this. We are saying that, nature does not say that, nature gives me the total force. But we can do that from our force point of view, so we end up getting this. Now comes the interesting points, you know. What is happening now? I will go to the next page and try to work on this part and see how this equation of motion comes about. So we end up getting something like Fi plus Fd plus Fr plus Fs, F hydrostatic S. So now here this is my incident wave force, this. So these two together quite often is known as Fe. Now it turns out that, let us first talk about this one. You see, it turns out that this force is proportional to Z. Okay. Why it is so? You can easily see. If I have this body, if I pushed it down to amount Z, then obviously the force is rho AWZ into Z. In other, if I push down 1 meter, it is actually TPC, tons per centimeter into Z, similar to that idea. So obviously it turns out this is linear with respect to displacement, hydrostatic pressure, linear with respect to displacement. Well, forget Z, let us take pitch or roll rather. What is roll? If I give a phi, what is my restoring moment? It is rho g v into zz. What is zz? For small angle, gm into theta. So it is rho g v gm into theta. So it again depends on theta displacement. So this is a proportional to z, okay, proportional to displacement in this case. Now it turns out, this concept we will tell much later on. It turns out that this particular force can be represented as a component in proportion to acceleration and a component in proportion to velocity. Actually it is like this. If I were to take this phase circle, and if this was my displacement z, remember this is my velocity this is my z dot dot. This is a standard harmonic equation. Now the force turns out is something like this vector, this radiation force. This is what it turns out, and one can show theoretically. So what has happened, this force has a phase gap, and what we can write, as you know, this to be vectorially I can write this and this. So I can write it this plus this vectorially, after all this is a vector. So this force basically is in, that means I can write this as a force proportional to velocity and as a force proportional to displacement. In other words, I can write this to be something like minus a, minus comes in, I will tell you why, something like that, some proportion. This I can write well as minus z. Actually always the minus sign comes because you know if I do plus z, force is in the other direction. So it looks like that. So now I reassemble that equation. Very interesting, I can find out that I can bring it on this side. So I end up getting an equation like m plus a z dot dot plus b z dot plus c z is equal to f e. And I will once again say this because this looks very similar to what you would have done anywhere. Okay. This is the general form of the equation, we will work on that later on. In here, please understand once again, these two are Fr and they are called radiation force. This is my hydrostatic restoring force, not hydrostatic force by itself, because remember that integration of pressure up to mean water line is balanced by weight. Archimedes said that long back. It is only that displacement, additional part, that has given additional pressure. That is why it is called hydrostatic restoring force, but not the Archimedes or buoyancy force per se. This is my, we call it wave exciting force. And this on, again classically this A is called, everybody knows this, added mass, and this B is known as damping, and this some people call it virtual mass, m plus a as virtual mass, you know, mass plus added mass as virtual mass, we can call it, depends on how you want to call it. So now we end up getting basically an expression which looks very similar to what you would find in any vibration equation. Mass into acceleration plus damping into velocity plus, you know, stiffness into displacement is equal to exciting force. So this is a single degree equation, freedom equation of motion. Now you may ask that where is the idea of you know, like multiple degree freedom equation of motion? It comes from here again. See, if I were to write Fr, Fr is radiation force, but it depends on acceleration velocity, but it may also depend on acceleration of other modes of motion. In other words, it may be a1 z, a z dot dot plus b z dot plus a1 phi dot dot plus b phi dot plus a2 theta dot dot plus b2 theta dot, etc., etc. In other words, this could have arisen because of other modes of motion. In other words, if I oscillated that in direction 1, it can be having some pressure on the other direction. So if I added all this up, similarly Fs is what we have seen earlier, that you know that if I give a roll, it has a heave. So if I have a parallel sinkage, it also has a trim. So you know that if I give a parallel sinkage, I have got rho g v into gml, but there is no, that is the trim, and I also have this rho g w into z. So these are the coupling. The coupling comes from here. If I were to add the full expression and bring it back, what would happen? There will be more and more term coming. That means in order to, for me to solve for z, I will have an equation where we will have z phi theta altogether. appearing in together. When you don't have, you have in isolation this equation. So what I end up getting, but that is one point, but what I showed here in principle how we are getting a kind of an equation of this form. So having said all this part, what has happened, we end up getting an equation of this form, which of course looks very similar, or it is same as any vibration equation, you know, m x dot dot plus b x dot plus k x equal to f. That is any forced vibration equation. Absolutely straightforward as forced vibration equation, you know, like this is same as m x dot dot plus b x dot plus c x equal to some f. We will discuss this in isolation for the specific cases. Where is the hydrodynamics lying? We will see that. This is also important for us. The hydrodynamic lies in this, because this is my radiation force and it lies in this. So if I look at this expression, if I break it down threadbare, mz dot dot is my mass inertial force coming from rigid body mass. As if I know mass, I know it all. Cz coming from hydrostatic depends only on the geometry of the hull, rho g, etc. Where is the hydrodynamics? It is here radiation force, it is here diffraction force. These are the parts, that is where hydrodynamics comes in. That means further break it down, added mass, damping. In here if you break it down, it will be diffraction force, and one can show they are connected. So this is where the you know, like hydrodynamic comes in. But what we will be doing is, we will presume as we go along that as if we know this, and we will talk about solution of this. You know, solution for this equation for the isolated cases of heave, pitch, roll is what we will discuss, and with a practical emphasis. One of the reason is because you actually would know solution for this pretty well. Everybody knows this, whoever has studied vibration, you know, any vibrating system. We normally do not like to call in ship motion as vibration, although the equation looks same. People call it oscillation because the periods are actually lower. Normally the word vibration give an impression of very high frequency, you know, like even ship hull vibration, but oscillation is slower. So this is only nomenclature. Remember, the equation looks same. Is a question of numbers, how the numbers look different and all that. Okay, so this is what we will talk about, you know, from I think I will talk about this from next class. But what we will do the next 10 minutes for this class is that we will try to go through a simple problem of what we did in last class on encounter period, just a simple problem, because that would be more logical, since I want to start now in isolated heave, pitch, roll, spending 1 more hour of lecture with all this thing. So having said that, now we understand the way it comes. We will start with that. This is a single degree of freedom. We will see how we can couple also and add it eventually. But for a class, it is extremely important to realize the component, where it comes from, how it comes from. Because you see, if you are able to guess A, B and F, others are much easily available. Hydrostatic tells you this, mass is known, then you know the solution. Solution for that will turn out to be fairly straightforward. So complexity is knowing this, which we will discuss you know, eventually. Okay. Having said that, let me just switch back because we also should kind of do some kind of problems as we go along. Let me just briefly go through a small problem on an encounter period problem, because encounter period is always important, since in all this again the oscillation period is always omega e. For example, here if I want to write, I should write this as something into cos omega e t plus something. So omega e is very important, it is that period. So let us work it out this thing. So it an encounter frequency problem. A problem on this. Now it says there is a 500-foot ship. Well, in ship many of the you know, like dimensions are still used in feet, although we should strictly use in SI units, but it is only for making a point. For example, knot will always be there, nautical mile. No matter what you say kilometer per hour, everybody will use knot. or nautical mile. This is proceeding, it says this is proceeding through a regular wave at an angle mu equal to 40 degree, heading angle of 40. Let me emphasize this part of heading angle, you know. In some reference book, you will find heading angle is defined between minus x axis, that is the opposite of the wave direction, and the ship, so that 0 degree becomes head waves. Okay. Some books, we are using opposite, we are using a consistent system where direction of V ship and direction of V wave, angle between that is mu. That is why for us 180 degree is this thing. Now here it does not say mu equal to 40 degree, actually I will tell you what it says. It says it is travelling with an angle 40 degree to the line of wave crest. So there are wave crests are there. It is travelling with an angle 40 degree to the line of wave crest. That means it is travelling with this as 40 degree. But remember, the waves are moving this side. So therefore the mu is actually 50 degree. The bow of the ship, it says the bow of the ship it meets successive crests at every 50 seconds, at 15 seconds. That means the crest takes 15 seconds to meet the bow. Now if you are an observer, you will see that every 15 seconds there is a bow coming. The other thing is, it says that the wave crest takes 10 seconds to pass the. That means it is something like that. You are standing here, you find that every 15 seconds a wave is passing by, and this crest is taking 10 seconds to pass the length. Find out the speed of the ship. What is V ship? See here, interestingly, what is given, see in principle what we will find out. It has given in a sense the wave speed, because it tells it takes 10 seconds to go, but not of course in a direct line, because the wave speed would be measured in a relative angle, that is wave is going to pass through this at a speed of Vw1 as V cos mu. Okay. So I have here Vw1 as V cos mu is the relative speed of the wave with respect to the ship. So mu means 15 degree here, and this speed, at this speed it takes 10 seconds to cover this length. That means what we end up getting is that this by here. Now here what would happen again is that this is going to be no here actually the thing is that no, there is the length is not going to, actually it is not this way, because see the ship wave is coming by that. So what is happening, that wave is passing from this line to this line here. So what happened, again I have to take this length that is taken is this much, it is not 500 but it is 500 into cos mu. So essentially it is 500 cos mu. That is what I was to say. Okay, I will tell you why, because what is happening, the ship is like that, crests are going like that, passing. So it is passing by this side, okay, and obviously relative speed is there, but this distance pass is this much. So it is basically this equal to 10 seconds. So from there we will end up getting, if I use this expression, we end up getting V W minus V cos mu into 10 equal to 500, which will turn out to be fit. So Vw minus V cos 32.5 15 feet. I am just trying to go slowly, and TE, encounter period TE is LW by VW minus V cos mu. This is 15 seconds. See, actually there are two information. One information is successive crest passing, that is going to TE. The other information is the speed. Essentially you have the two information given, TE and V. So from there we have to just figure it out. So this is this relation, and that tells us from here LW equal to TE VW minus V cos mu. This is 15 into, this is 482.25 feet. So VW equal to G into LW by 2 pi. This is going to give us 49.71 feet per second. Okay. So this is VW. Now we need to find V ship. So we have VW minus V cos mu equal to 32 point, that's we had here this relation 15 feet. So from there minus V cos mu gives you this, gives me, I think there is a space here, V equal to 27.32 feet per second is equal to 16.17 knot. I mean, it is very straightforward problem. What I wanted to tell is two things here, that in this kind of problems you have two information. One was the encounter period TE, one was the speed. All that one has to do is to figure out the relations properly, and therefore you can work it out. Now a similar thing may occur. For example, many times the questions are asked on this or on this. There is omega E versus omega. See, for example, we may say that simple question is of course the simplest one, that if I have omega T given, or normally what would happen, we may say that ships and waves are traveling in the same direction, say that means mu is either, see there is sometimes problem like that. If you are standing here, you are finding out that wave crests are passing by you at certain speed. So in such problems I had mu given, well actually it may pass by or may go this side, you do not know. Sometimes the problems are given that way, so it can be 0 degree or 180 degree. Now omega E is given, find out omega. Well, we go to this relation omega equal to omega minus omega square by V G, and cos mu is given here is negative, so it becomes, well, cos mu is, there are two cases, it can be this or it can be, sorry, G V here, G V here, and since the quadratic equation you end up finding out two solutions for omega, and then once you know the omega you may figure out lambda, then you can tell what is the length. So these are very straightforward problems though, but one thing we must realize is excitation frequency. That is what I am emphasizing it. If you have an instrument here, you are measuring excitation, okay. So what is happening, I end up finding out that my body has an excitation of this period TE, some T, say 8 seconds or whatever. Please understand that this 8 second might arise if it is a following wave from multiple scenarios, okay, because if it is a following wave I could have 2 omegas which could have given rise to 8 seconds. So unless I know that, I really cannot figure out the motions properly. So there are multiplicity in following wave conditions. Same excitation may occur from more than one wave condition. In fact, typically what happened, one at a shorter wavelength, one at a very long wavelength, similar results will come. We keep doing these problems. We could have also done this here. See the quadratic equation relation, right? See, omega E is omega plus, let me write it down, this is V by G into V. We can easily solve it by putting some number and see there are two feasible omega number. Now what would happen? What happens in this kind of case? In a problem, what happens in this kind of cases? I give an omega, let us say omega E, which turns out to be somewhere here. Then of course what will happen? If you will solve, you will find out you have imaginary numbers of omega. Means you will tell that such omega E cannot occur. Simple as that. Okay, that is one thing. Now we have found out also, let's put this number. What was this omega? This omega was G by, sorry, this omega was, let me just tell, because I want to spend this few minutes on this number here. This is G by 2V cos mu, G by 2V. Okay, this was G by V cos mu. Yeah, okay. Sorry, sir. This is G by V cos mu. Okay. Now see, just simple thing. Say cos mu is equal to 1. Okay, so it is, let's say G by V in a following wave condition. What can be the possible number at which this occur? That's very important. Just physically understanding. Take V equal to let's take some feasible number. V equal to say 20 knots, 10 meter per second. Okay, say 10 meter per second. G will be about 10. So G by V becomes about 1. So omega becomes 1. So what is T? 2 pi by omega. So about 2 pi second. What is 2 pi second? Is about 6.28 second. How much is the length of that? 1.56 into 6 square. That is approximately equal to 36 into 1 and a half, about 50 meter. So you see, for a 50 meter long wave, for this particular case, you end up getting, for following wave, 0 encounter frequency. So it is very feasible range. That means 50 meter wavelength is possible, and there can be a small frigate going at 20 meter per second. So in other words, in realistic waves do exist coming from following wave, which can lead to negative encounter frequency, which can lead to 0 encounter frequency. It is not outside my practical bound. This is important, which means I cannot ignore it if there is a following wave coming. It is a practical scenario. Waves are there 50 meter, 100 meter, 200 meter, etc. Anyhow, so we must realize this, but having said that, once again I tell you that as importance is more on head waves, we are going to give less focus on following waves as such, as far as motions are concerned. With that, I am going to end this today's class. I will go tomorrow on these individual modes of motion. Thank you.